Retries can look like an easy reliability win, but when they pile onto a failing system, they burn tokens, add latency, and may duplicate side effects. In this lesson, we'll make retries disciplined, bounded by deadlines and cost, prioritized by importance, and made safe through idempotency. So far, we've looked at why LLM apps fail, how to redesign the serving stack, and how to harden reliability. Caching, deduplication, circuit breakers, and fallbacks already reduce waste and contain failures. Now we go one layer deeper. When failure still happens, retries need to be controlled by deadlines, budgets, and safe idempotency boundaries. At first, retries feel harmless. If a call fails, just try again. In an LLM workflow, though, one retry can repeat model tokens, retrievals, validators, and tool calls. During an outage, that can become a storm. Higher bills, slower users, overloaded services, and duplicate emails, tickets, or writes. A retry budget is the guardrail that keeps retries from amplifying an outage. Instead of asking, "Should we try again?" the system asks, "Is another attempt still worth it?" The policy can cap total attempts, added latency, token spend, downstream calls, and whether the operation is safe to repeat. A high-value, time-sensitive request may earn a small budget. A cheap background task may get more patience. A risky side-affecting action may get none. This keeps transient failures recoverable without creating runaway cost or cascading load. These budgets should be treated as product policy, not just engineering defaults. A free, low-value request might get one quick retry, then fail gracefully. A paid or enterprise workflow may justify more attempts, a higher cost ceiling, and a stronger fallback path. Timing matters too. Interactive requests need tight latency limits because users are waiting. Background and async jobs can retry over a longer window without hurting the experience. The important rule is to make these policies explicit, versioned, and observable, so teams can see who gets which retry behavior and why. Before any retry, make a budget check, not a reflexive repeat. First, ask how much user-facing time remains. If the deadline is 2 seconds, and the first attempt already used 1.6, a retry expected to take 900 milliseconds cannot help. Even if it succeeds, it arrives too late. Then check cost. Another LLM call may spend tokens, retrieval, GPU time, or provider fees. After each failure, both budgets shrink. Retry only when there is enough time and enough cost for a meaningful second attempt. Otherwise, fall back or fail fast. LLM retries should be selective because every attempt adds latency and cost. Treat rate limits, connection resets, brief 5xx errors, and timeouts before generation as retry candidates, usually with backoff and jitter. But do not retry deterministic failures, bad request format, auth problems, schema invalid prompts, or context length violations. Those need correction, not repetition. Also factor in model tier and provider health. If a premium model is degraded, fallback routing may beat repeated retries. For long context or high token jobs, keep the retry budget smaller. A timeout is not just an API gateway setting. It is request context. When the request enters the system, create a deadline from the product SLO, then pass it into retrieval, re-ranking, inference, tools, validation, and persistence. Each component should ask how much time is left before starting costly work. If only 10 milliseconds remain, launching another model call or database write is waste. This prevents zombie work, protects capacity, and keeps downstream systems from spending money after the user has already given up. Timeouts and deadlines answer different questions. A timeout is local. This service will wait up to 10 seconds, regardless of what happened before. A deadline is global. The user's request must be done by a specific time. Problems appear when services stack their own independent timeouts. Each hop may behave correctly, while the overall request has already missed its promise. In production, pass the deadline along with the request. Then each service calculates the remaining time and chooses a smaller, realistic timeout, or stops early. For retries, treat the deadline as absolute, not as a fresh timeout for each attempt. Before every try, compute the remaining time and compare it with the minimum realistic cost of trying again. That estimate should include backoff, model inference, validation, persistence, and any cleanup. Keep a small buffer for fallback because returning something controlled is better than timing out blindly. If the remaining time is below the estimated attempt cost, stop the loop immediately. Do not spend compute on work that cannot finish. Retries help only when they reduce pressure instead of amplifying it. Immediate retries can turn a small failure into a retry storm because every client asks again while the service is weakest. Exponential backoff improves this by waiting longer after each failed attempt, such as 2, 4, then 8 seconds. But if all clients follow the same schedule, they can still create synchronized waves. Jitter fixes that by adding random variation, spreading retries across the window. Always cap retries by the remaining deadline and your retry budget. Choosing a jitter strategy depends on the risk you are managing. Full jitter gives the widest spread, so it is safest when many clients may retry at once. Equal jitter keeps delays more predictable, which helps when latency deadlines are tight, but it spreads traffic less aggressively. Decorrelated jitter uses the previous delay to avoid clients falling into the same rhythm again. Whatever strategy you choose, set a maximum backoff and stop when the deadline or retry budget is gone. Jitter reduces pressure. Limits protect the user experience. LM workflows often do more than generate text. They send emails, update CRMs, create tickets, charge cards, and write to databases. If orchestration retries after a timeout or partial failure, the model step may run again and call the same tool twice. Idempotency makes those retries safe. Each logical action carries a stable idempotency key. The downstream service checks whether that key has already been committed. If not, it performs the action and stores the result. If yes, it returns the previous result without repeating the side effect. Idempotent tool execution starts by separating decisions from consequences. Let the model propose candidate actions, then validate them against policy before anything touches an external system. When an action is approved, assign a deterministic operation ID built from stable inputs like user, workflow, step, and action type. Store that operation state so retries can resume, skip duplicates, or surface failures safely. For APIs that are not idempotent, add your own wrapper. Record intent, call once, reconcile outcomes, and compensate when needed. The goal is simple. Retries should never multiply real-world effects. Safe retries are not just try again. They need boundaries. Budgets limit extra work, deadlines stop pointless work, jittered backoff spreads pressure over time, and idempotency makes repeated attempts harmless. Together, these controls turn retries from a risk into a reliability tool. Next, we build on this foundation with load shedding, priority handling, and safe concurrency.